Thank you all for coming. I'm going to talk about coding for information storage. With the explosion of information in nowadays, the storage of information is becoming a really important issue. And in this talk, I will talk about two separate subjects. The first one is on system level, which is coding for distributed storage. The second one is more on physical level, which is some modulation scheme for flash memory. Data center today is becoming larger and larger, and they're in the form of warehouse size and also distributed manner. So in such a large scale, failures are inevitable. Every day you see lots of failures from data centers. And here we define a failure as a complete loss of all of the information from a storage node. You can think of a storage node as a hard disk, for example. Or sometimes you can think of it as a whole stack of hard disks. And in such scenario, of course, you don't want to lose your information. Storage is a little bit different from communication in the sense that if you lose something, then you cannot recover it. But in communication, if you lose the transmission, you can ask for retransmission. Therefore, we have to protect data using some kind of redundancy. Or in my language, it's like coding. And with a certain amount of redundancy, if something happens, then if you lose something, then you need to do decoding and recover the information. So it's you need to maintain the data. And the question is, what is the trade-off between the cost to maintain data and the amount of redundancy you need in your code? So let's look at a very simple example. The simplest way to protect the data is backup. So suppose that I have 3 nodes. Each node has 1 bit of information. So you have A in the first node, B in the second, and C in the third. Now, to protect data from failure, so what I do is I add 3 more bits and 3 more nodes. So now if I have a failure, or if I have an erasure in one of the nodes, I can of course recover the information. We say that, so we'll talk about it. So then we can do something a little bit smarter than simple backup. So we call it coding. In the same example, if I have 3 bits, I can add 1 extra bit, which is exclusive OR of A, B, and C. And now, if I lose one of the nodes, what you can do is you can subtract B and C from the redundant node. And now you can recover the information. We say that in the first case, the number of redundant nodes or storage is 3. In the second case, the redundant storage is 1. So let's look at how can I maintain the data. So in the first case, if I lose A, what I do is I read the value of A, and then I can recover. So I say that the access ratio is the number of accessed nodes, or the number of read nodes, divided by the total number of remaining elements. So it is 1/5 in this case. Suppose that I lose the first node, what I do in the data center is I buy a new disk and put it there and try to store the value of A. So what I do is I transmit the value of A to my new disk. So we say that the bandwidth ratio is the number of transmitted elements divided by the total number of remaining elements, which is also 1/5. In the second case, in order to recover the value of A, I need to read all the remaining elements. And then I need to transmit all these values to my new disk. So I say that the access ratio is equal to the bandwidth ratio is equal to 1. This here. Okay. We also define some other parameter, which is the number of touched nodes. We call it D. So here, D is equal to 1 because I only look at 1 node. And in the second case, the number of touched nodes is 3 because I look at all the other 3. Now we ask the question, suppose that I want to use a code that has smallest redundancy, which is like in the second case. And then we ask, how can I lower the rebuilding ratios? Okay. Obviously, in this case, there is not much you can do. The rebuilding ratio has to be 1 in the second case. Okay. So the problem that I just talked about was first called repair problem, and it was proposed by DeMarcus et al. In 2007. They show that using network coding type of argument that you can derive some cut-set lower bound for the rebuilding ratios. And suppose that you have a code where you have k number of systematic nodes or k number of information nodes and r number of parity nodes or redundant nodes, then the lower bound of the bandwidth ratio is 1 over r. Okay. There are lots of work following to this pioneering work by DeMarcus. The first set of work is called minimum bandwidth regenerating codes. So they are the kind of code that tries to achieve those lower bounds where you try to get smallest bandwidth possible. The second group is called minimum storage regenerating codes. And these are the codes that we're going to talk about. Those are the codes that have the smallest redundancy. And then they try to minimize the bandwidth after that. So there are quite a few works. The first one is by Knickknack et al. And they did a computer search and showed that for the special case of total of 5 nodes, then there exists a code that matches the bound. And then there will work for the case where k is less than r, which means you have a small number of information bits and a lot of number of redundant bits. In such case, there are codes constructed by Rashmi et al., Su et al., and Rashmi et al., and they show that the lower bound is achievable. Then for asymptotic results, Kadambi et al. And Su et al. Showed using interference alignment technique that the lower bound is asymptotically achievable, which means when you make each node very large. So in the example, we have each node have only 1 bit. But in this case, if you make each node very, very large, then you can approach the lower bound as closely as you want. In the last case, which is what I'm going to talk about, is the case where k is larger than r. So that means I have a lot of information and a small amount of redundancy. So in this case, I think it's more practical in a lot of storage, especially for archive kind of data. So in this scenario, the lower bound was achieved by 3 independent but actually equivalent works by Kadambi et al., Papadopoulos et al., and us. And I will talk about our construction that was involved here. So the rebuilding problem has gained a lot of interest in the recent few years. And I think because it is kind of a simple and also practical setup, and also it connects very well with the network coding results. And besides the storage redundancy and also rebuilding ratio properties, there are also a lot of other properties that people look at in distributed storage. So for example, people look at how do I put information in the different nodes. Maybe I don't put in each node the same amount of information. Maybe the first node I put 5 bits, the second node I put 3 bits, and so on. And this is called the allocation problem. The second one is locality, meaning how many number of touch nodes do I need in order to recover a node. In our previous example, for the backup, we touch only 1 node. For coding, we touch 3 nodes. So maybe you have something in between and a lot of such kind of problems. So that's called locality. The third one is availability, which means if I lose a node, how many different ways can I recover it? In our example, we have only 1 way to recover it. But maybe you can design a code that is similar to locally decodable codes, for example. Then you can have a lot of different availabilities. And then there is a queuing problem, which means the users would request files from the nodes, and then the nodes basically have a queue in front of them trying to serve all the users. And in the end, there's also security problems. That is, if you have eavesdroppers or if you have adversaries, then what is the ratio in that case, and what is the storage in that case? So in order to get the lowest redundancy, we use the code that is called MDS, which means maximum distance separable code. And this kind of code is equivalent to say that if a code has R redundancies, then it should be able to correct R erasures. So here is an example. Suppose I have two information nodes or systematic nodes. In this example, different from the example we had before, each node is a vector instead of a scalar. So now I have 2 bits, or 2 bits in the first node and 2 bits in the second node. And then you have 2 parity nodes, which is some exclusive OR of some of the bits. Okay? We claim that this code is MDS, meaning that if I lose any of the two nodes out of 4, I can recover the entire information. So here is an example. Suppose that I lose the first 2 nodes. What can I do? So I read and also transmit all of the remaining elements. And then I claim that I can recover the information. This is because from C plus B and C plus B plus D, I can recover B. And then from B, I can recover A, and from A, I can recover D, and then so on. So then you can recover everything. In this case, the access is equal to the bandwidth, is equal to 1. But in practice, more often you would see only one erasure in the system, because in the end, failures are kind of not as often. So now suppose that I lose only the first node. Do I need to access all the remaining elements? How can I recover the information? Notice that in this case, I don't want to recover the entire file. I'm only interested in 2 bits. So, any guess? Who thinks I need to access 6 elements? Or 4 elements? Less than 4 elements.
至少需要3步吧。这个 A 加 B 加 D 减去 A 加 D， 就先把 B 给恢复了，然后再由 B 导出 A， 再由 A 导出 B， 就能省掉 C 加 D 这一步，就不用恢复 C 了。哎，哦，不对，你要恢复的是 AC 是吧？
对，就是你已经有 B 跟 D， 你现在只想恢复 A 跟 D。
啊，那就2步就行了。
啊，所以需要，你说需要几个？
就是几次访问是吗？
需要几个比特
？2个比特。哎，
需要访问几个比特？
你怎么叫一个比特？
就是我
A 算一个 ，B 算一个，
这算一个，这算一个，这算一个。
4个需要。4
个比特。
对。
Anybody thinks less than 4? So this is the solution. You can actually read only 3 elements. From this 2 you can get A, and from this 2 you can get C, right? So, excuse me. So in this example, the access is equal to bandwidth is equal to only 1/2. For another example, suppose I lose the last node. Now how many do I need to read? Can I read only 3?
干嘛要恢复？不是已经全
A、B、C、D 都已经在了。
But I want to maintain the code, which means 就是说我丢了最后一个，就是我需要这个 node， 需要这个 code 仍然有2个 redundancy。我丢了这个 redundancy， 但是你如果再丢一个就没有办法。所以我现在就是丢了的时候，我仍然需要把它恢复出来。但是我只需要恢复这个比特的，就是这个和这个。
应该是3次吧。
3, anybody think 3?
肯定是3次，肯定是3次，就是找出哪3个来。
Actually, this is 3, 4. So, I tried all the combinations, but maybe you can find a case where you get C. Actually, here you have to read 4. But the trick is here you can transmit only 3. So here you do an exclusive OR of these 2 bits, and you get A plus B plus C plus D. Okay? Now you can recover these 2 bits. So in this example, the access is equal to 2/3, but bandwidth is equal to 1/2. So we can see that all the time, access is larger than or equal to bandwidth. And usually, the bits that you transmit is something that you compute, and then, so basically it's a function of the node, of the element that you read. So this code is called even-odd, and it is the building block of the read systems for hard disk storage. So I'll talk one word about the difference between access and bandwidth. If you think about a network of storage nodes, then usually the traffic is going to be the bottleneck of the system. Therefore, we would like to have small bandwidth. On the other hand, if you have centralized storage, where you think of all the disks or all the nodes in the same drawer, then they are very close to each other. Therefore, the reading would be the bottleneck of the system. Therefore, we would like to have a small access. But of course, optimal access has an advantage because it means optimal disk I/O, and it also means you don't need to do any calculations within a surviving node. So you read something and then you transmit directly. Okay? So here is how we're going to try to approach this problem. So we try to construct a code that is MDS and also has low rebuilding ratio. And we use code where every node is a vector. So we don't want to use a scalar because as the example we showed before, scalar will not work. So let's say that I have 4 rows, or each node is 4 symbols. So now it's not bits, but it's some symbols from finite field. And then we have, let's say we have 2 parities. The first parity, I'm going to construct it similar to the even-odd code, which is the sum of the row, or linear combination of a row. So R0 is a linear combination of A0, B0, and C0, and so on and so forth. The second parity, I'm going to construct it as some arbitrary line. So instead of a straight horizontal line, I will use some arbitrary line, and we call it zigzag sum. So for example, I will, right now I'm just drawing lines randomly. So let's say I draw a line like that, and I say the Z0 is sum of those, or linear combination of those elements. And then I can have, similarly, some other parity elements. Okay? Now, notice that after this construction, every information column is a permutation of the 4 colors. So for example, the first column is a permutation, blue, green, purple, and red. So let's first replace all the colors with some numbers, so things look more mathematical. So I replace the first one with 0, and then 1, 2, and 3. So now the numbers represent the colors, and also every column here is a permutation of the row indices from 0 to 3. For example, column 2 is a permutation, 3, 0, 1, 2. Okay? So once we have this code with this peculiar structure, then we ask, how do I do rebuild? So suppose that I lose the first node, and I only want to recover those elements. What can I do? Well, the naive way is I can read column 1, column 2, and the row sum. Then I can subtract column 1, 2 from the row sum. Then, of course, I can recover the information. In this case, I need to read 12 elements. However, I can do something smarter. So again, guess, how many elements do you think I need to read? So in this case, actually I can read only 8 elements. So those highlighted ones. So R1 is the sum of the line number 1. So I can recover the value of 1. Then I can from R3 recover a value of 3. Z0 is the sum or linear combination of elements that are labeled 0. So I can recover 0. And at last, Z2, I can recover purple dot 2. So you can see that in this example, I use some of the rows and also I use some of the zigzags. And the rows and the zigzags that I use completely intersect with each other. And that is the reason that we can save in the number of reads. In this case, I only read 8, which is half of the remaining table. And by the lower bound, of 1 over r, where r is 2. So this construction is optimal. But we want it to be optimal for any of the nodes. So let's say that I lose node 1. Then how many do I need to read? Well, the smartest way that I found was 9. So maybe you can find something better. But I tried and I only find 9. So similar to the previous example, we can use some rows and some zigzags and recover. So here the rows and zigzags do not completely intersect. So now we come to the question, are there permutations such that for any node erasure, we can always read only 1/2? And here is the solution. So this is how we define permutations. Suppose we have 4 rows and 3 information columns. For column 0, I'm going to use the identity permutation. For column I, I'm going to flip the ith bit as follows. So I read the row indices, change it to binary, and then for column 1, I would flip the first bit. So I would get 1 0 1 1 0 0 0 1. And now I change it back to integers. So this would be my permutation. Okay. Similarly, for column 2, I would flip the second bit. And now this is my permutation. So here you can see that among all the 4 factorial, which is 24, I use only 3 of the permutations. And they have a very special structure that actually depends on the binary representation of integers. So here is our code. So on the top table, we have the zigzags. Here we'll show the actual content. So here each symbol is some value from a finite field, and actually we use finite field of size 3. So every symbol here is either 0 or 1 or 2. Okay. Notice that here, okay, so let me first show an example. So Z2 is the sum of elements labeled 2. So here it's p plus a plus x. Notice that some of the coefficients are 2 instead of 1. I have 2 here, but 1 here. And this is, we will explain it a little bit later. The code has the properties that first it is systematic, meaning that all the information are stored in the first 3 nodes, and all the parities are stored in the last 2 nodes. It is also the so-called optimal update, meaning that if I want to update the value of one of the elements, I only need to update it 3 times. So for example, m is only changed 3 times in the table. And this is optimal because this code is MBS. Suppose that m only appears twice in the table. Now if I lose this column and that column, I will lose the value of m. Therefore, m has to appear at least 3 times. So we say that this is optimal update. The reason that we want optimal update is because we want to be able to rewrite the values as fast as possible. Okay. So maybe we look at the examples that we had before. Repetition code is optimal update. One parity code is also optimal update, but in-out code is not. Because here, if you look at D, it appears 4 times in the table, which is larger. And the reason that you actually does not have optimal update is because this code is binary. And in our code, we have ternary codes, basically. So now let's look at the code that we have constructed and check what is the rebuilding ratio. So suppose that I lose column 1. What you can do is you can access those highlighted elements. And from R0, you can get 2. From R3, you can get 1. From Z0, you can get 0. And from Z3, you can get 3. Okay? Similarly, if I lose column 2, I can read these elements. And then, again, using 2 rows and 2 zigzags, I can recover all the entire column. So let's look at a larger example where I have 4 information columns. In this case, the number of rows grows exponentially. It is 8 rows. So here are the permutations. Again, the first permutation is identity, and the others are flipping some corresponding bit. So suppose that I lose column 1. then you can check that if I read half of the table, I can recover it. So now we ask the question, is this code MDS? We have so far tried to recover only one column erasure. Now suppose that I lose 2 of the columns. Then because the code is MDS, I have to be able to recover them. And if you look at this example, I need to recover 8 unknowns. And basically, I have 8 linear equations to solve. And if we use a more number of systematic nodes, then the number of equations will grow exponentially. However, because we have chosen the permutations in this very particular way, then the equations that you solve for every time you only need to solve 4 of them at a time. So basically, these equations, you can separate them into smaller systems. So for example, here, I can first solve for MAPC. And because I chose the coefficients in this way, some of them are 1, some of them are 2, you can show that by our algorithm, the equations are linearly independent. Similarly, I can solve for another 4 elements, and they are also solvable. So we have shown that the code, we call it a zigzag code, has optimal ratio of 1/2. It has finite field size of 3. And as I said, binary code will not work. So this is also optimal size. And at last, the code has an exponential array size. So here, the array is 2 to the m times m plus 1. And actually, for our constraints, this is already optimal. Even though it's very narrow, we cannot do much about it. But if you think about practical storage node, which you can think of it as a disk, then it could be 1 terabyte. Then basically you can have, for each node, for this kind of size, then you can support maybe 40 nodes in the system, which is relatively enough for storage. So we have some generalizations of the zigzag code. First we ask, what if I have more than 2 parities? And what if I lose more than one of the nodes? And we were able to show a lower bound and achievability that the number of access is the amount of access is E over R, where E is the number of erasures, R is the number of parities. And also, in our code, we first only tried to review the systematic node. Now, we try to also review the parity nodes. And we have constructions for that. And in the end, we also asked the question, the array is narrow, but can you sacrifice some of the good properties and make it wider? And we were able to do this. However, this kind of array is still sort of like exponential times some number times some constant times n for a small number of parities. So, and also, inspired by the previous construction of the wider array, we asked, given that I have 2 parities and 2 to the n number of nodes, then what is the largest number of columns you can achieve under different constraints? Maybe you want optimal bandwidth, optimal access, optimal update, or non-optimal update. And we were able to show that in 3 of the cases, this access and bandwidth code, optimal access and optimal bandwidth code have exactly the same array size. But in this case, access and bandwidth are not equivalent. We noticed that in a lot of constructions that were done before that were aimed to get optimal bandwidth, they actually also achieved optimal access. But this result showed that these 2 metrics are not the same. So now I'm going to talk about a different subject, which is also a coding problem with a flavor of combinatorics. It's called rank modulation for flash memory. So flash memory has increased in the market exponentially in the recent years, and especially in personal uses. So you can see flash in your computer, You can see it in your cell phone and cars, but it is still too expensive and also not reliable for industry uses. So you don't see a lot of flash in data centers, for example. Like the example, the code that I talked about before, I always say hard disk because that is what happens more often in real systems. So the question is, what can we do to improve the performance of flash such that it can be used in data centers? And the reason that we want to use flash, of course, it has smaller space, and also it does not require as much cooling, and also save a lot of energy in the data centers. So I claim that the so-called rank modulation scheme is going to be a very good candidate for flash. So I will talk about it in more details. So first, let's see what's the drawbacks of flash that prohibits us from using it. Flash got its name because whenever you try to erase something, you erase in a flash. So for example, every time you have to erase a whole block of transistors or cells, and you cannot erase selectively. So here, each square is a transistor that has a special floating gate that can hold electrons in it. So according to the amount of electrons, then you can tell what is the information that is stored. So maybe you have a small amount, it says 0, then it says 1, 2, and 3, and so on. So we say we call something an erasure, means we try to take electrons outside of the transistors. And we say program, meaning we want to put electrons in the transistor. Sometimes I call a transistor a cell. So here, suppose that I want to erase one cell, you have to erase a whole block. And typically a block would contain 10 to the power of 5 number of cells. Similarly, if I want to decrease a cell level, suppose I want to change from value 2 to value 1, then you also cannot do it selectively. So you have to erase the whole block, and everything becomes 0, and then write everything back. So this, of course, is very costly in terms of energy and time. But also, more importantly, it also affects the lifetime. Because for flash, you cannot program and erase more than 10 to the 5 times. After that, there will be too many errors in the device, then the chip will be useless. So we want to avoid erasure as well as try to avoid decreasing the cell level. So there are some works that are done in order to avoid erasures, and there are two solutions. The first one is the so-called rewriting codes, which tries to write as many times or program as many times as possible, and erase only after a lot of number of writes. The second is rank modulation, and I will talk more in details about it. So maybe I'll skip the rewriting example. So let's first look at how information is represented traditionally. So as I said, a certain amount of electric charge will correspond to a certain message value. And so for example, suppose I want to write the message 3. So I want to put electric charge up to here, and this will be my cell. Then people use iterative writing scheme. First they put some electrons in the cell, then they put some more, and put some more very carefully until they reach the target. If you're not careful enough, you put too much, then you have to decrease. And as I said, decreasing is very expensive, and we want to avoid it. That's why you want to write very carefully a lot of steps. And typically, for writing, people will take 7 or 8 number of iterations. So this will largely affect the writing speed of flash. Another problem of flash is charge leakage. So suppose that I have already some information stored in the cells, and I put the flash unplugged in room temperature for a while. Then some of the electrons get to go outside. Then you will see possibly different numbers that you stored. Therefore, you will see some errors, and we say that data reliability is affected. So therefore, Andrew Andrew Jiang and et al. Proposed rank modulation in 2008. It uses relative values instead of absolute values to represent information. So now I don't have fixed levels that represent different messages. I only have some permutations or ranks out of a group of cells, and that will be my message. So here is an example. Suppose I take 5 cells, and I want to get a permutation. So I first take the highest cell, the second highest cell, the third one, and so on. So my permutation is 5, 2, 4, 1, 3. So every permutation will correspond to a different message. So notice that here, rank modulation is different from traditional modulation in the sense that I look at a group of cells and I don't have target level. If, for example, I happen to make a mistake and cell 3 goes too high, then simply I can raise all the other cells such that the rank is not affected. Therefore, you can write in a very fast manner. And also, if the charge gets outside in a relatively same manner, then the permutation will not be changed, even though the charge is different. Therefore, you won't see as often an error in the data. So we say that rank modulation improves the writing speed and also reliability of Flash. However, as we saw in this case, the decoding of a permutation takes about n-1 iterations. And the question is, how can I reduce the decoding complexity? But of course, I need to sacrifice something. So here, I propose partial rank modulation. So I take a group of M cells. Instead of taking a full permutation, I take a partial permutation. So let's say that I look at top k out of n cells. Say k is 3. So I would get 5, 2, and 4. And I don't compare 1 and 3. So in this case, the ordering of 1 and 3 could interchange, and only the top 3 cells represent the message. In this case, the capacity is smaller. It's 5 times 4 times 3. And we have a lower decoding complexity, which is k. So now I ask the question, how do I update information? But I don't want to do erasure. So basically, suppose I already have a permutation representing some message. Now I want to change it to a new message, but I don't want to take electrons out. So this is what we can do. Suppose that I have 5, 2, 4 in the beginning. Now, I push cell 1 to the top and get a new permutation, 1, 5, 2. So I get a new message without erasing, and I only operate on one of the cells. We call this push to the top operation. So basically, we take one of the 5 cells, push it to the top of the whole group, and it's a very simple transition. So we see that after this operation, there is a gap between cell 4 and cell 3. Similarly, suppose that I push cell 2 to the top, then I will see a gap between 5 and 4. But because we use the top 3 elements, we don't want there to be a gap. So we say that I will only push cells k plus 1 up to m to the top. So after defining partial rank modulation and also push to the top, we define some combinatorial objects that we want to construct. We call it gray code. So basically, it is a cycle that contains all the k partial rank modulations once and only once. So, and also the cycle has transitions from one permutation to another, and the transitions are pushed to the top. So here is an example. Suppose I take a group of 3 cells. I could either push 3 to the top or push 2 to the top. So here I would have a graph where the nodes are the permutations, the vertices are the permutations, and the directed edges are the push to top transitions. And every node will have 2 outgoing edges. So you will have a graph that looks like this. Now we ask the question, what is a gray code? In this case, a gray code corresponds to a Hamiltonian cycle of the graph, which goes through all the nodes in the graph exactly once. So actually in this code, in this graph, you can find 3 different Hamiltonian cycles. So you have this one, or this one, or this one. For a larger example, suppose that I have 4 cells, and I want to build a graph for that. And suppose that k is equal to 2. So I don't care about the orderings of the lower 2 cells. So in this case, I can push 4 to the top, 2 to the top, or 3 to the top. And I can have the whole graph. A gray code here would correspond to a cycle that contains half of the nodes. The reason is that the value of the 2 lower cells can interchange with each other. So you can check that every 2 out of 4 partial rank combinations is represented exactly once in this cycle. So every 2 out of 4 number combinations appears here. So what can we do after having this strange cycle? So we say that we're going to build a counter with it. A counter basically counts from 0 to 1 to 2 and so on. And similar to binary counter, here we use, instead of binary numbers, we use permutations to represent integers. And from one number to the next number, we will use push to the top. For example, suppose I start with the cycle from this one, 1, 2, 4, 3. So that would be the numbers of the cells. And I say that permutation corresponds to value 0. And then, following the cycle, I will go to 3, 1, 2, 4. And this would be my second permutation. And I say that corresponds to 1. So from 0 to 1, I only push 3 to the top. Okay? And similarly, we can go all the way following this cycle and count integers, in this case, from 0 up to 11, and then back to 0. Every step here, you only push 1 cell to the top. And this is a very simple operation. Combining this counter with some other techniques, such as the rewriting code that I talked about, we are able to build a system for Flash where you can write arbitrary message a lot of times before you need to erase. Here you cannot write arbitrary message. You can only write from 0 to 1 to 2. But combining with rewriting codes, we can jump from 0 to maybe 8 and then jump back to 2 and so on. But every time you only increase a little bit, and then maybe after 100 rewrites, then you only need to erase that. So the general construction for arbitrary value of m and k is as follows. I first define some equivalence class of the partial permutations, and then construct some generation tree that goes through all the classes. A related notion of gray code is the so-called universal cycles. It is a cycle that contains all the k partial rank modulations exactly once as a subsequence. The definition is very similar to gray code, and here we show an example. This is a sequence, or if you look at it with wraparound, it's a cycle. And now I take all the subsequences of length 2. So I get 2, 1, 1, 3, and so on. And with wraparound, I also get 1, 2. You can check that every 2 out of 4 permutations appear here exactly once. So this is a universal cycle. Universal cycles was proposed by Trun et al. For more general subjects, and the existence for partial rank modulations was shown in 1993 by Jackson. But explicit constructions was only known by Rusty and Williams for the case of full permutations. But in general, people did not know what is a good construction for arbitrary partial rank combination. And it turns out that gray code is actually equivalent to universal cycles, and our construction solved this open problem. So actually, we didn't know about universal cycles until we finished the work for Flash memory, and then and then one of our friends, who is an expert in combinatorics, pointed out that there is an open problem here. Maybe your work actually fits here. But also, actually, there is an open problem for universal cycle constructions, where instead of looking at permutations, they look at combinations of k out of n. And people don't know whether those cycles exist or not, and not to mention constructions. So here I come to my conclusion. There are lots of open problems and interesting subjects in distributed storage and flash memory. But here I only focus on the problems that are related to my particular subjects. For distributed storage, we don't know what is the actual rebuilding ratio if I have limited field size and limited column size. So we have an array that is like exponentially long. But if I want only square matrix, square arrays, say, then people don't know whether rebuilding ratio should be 1/2, should be 3/4, or maybe it should be 1. Then also, it would be interesting to be able to rebuild a given code, for example, Reed-Solomon code. That is because those codes are very widely used in real systems. And if you can decrease the ratio from 1 to 3/4, that means you actually benefit a lot. For example, in Facebook, the rebuilding traffic takes up about 30% of all the traffic in their storage cluster. So you think that they get information from users and send information to the users. That would be a lot of traffic. But actually no, because they use Reed-Solomon code and they don't have a good rebuilding strategy, they actually need to pay 30% of the entire traffic for rebuilding only. And for partial rank modulation, the scheme that I showed did not have a good simple mapping between integers and permutations. And also, because we don't use the lower m minus k cells, it would be very straightforward to try to use them for redundancy or for error correction. And that would be a very interesting open problem to work on. And here are my collaborators on related subjects. Thank you all for coming.